Hey, this is my introduction to mathematical proofs playlist. We'll be talking about numbers. Actually, what are numbers? So we introduced the language of sets last time, right? And now we'll talk about numbers as a set. Because a number is just an element from a set of numbers, right? Throughout this lecture, we'll take a trek through the advent of numbers to ancient Greece on our quest to explore what numbers really are. So we have many different types of numbers. That's something you'll see. And you'll actually see why in a bit, right? So the first most common numbers is we call it counting numbers, what I've been calling the positive non-decimal numbers this whole entire time, which is the natural number. And we use this weird looking n to denote this. In the last video, I never really explained what it is, but you should have seen this from the last video. So you might be wondering, why would we do this? Well, we count stuff. There's one thing, two thing, three thing, four thing, five thing, and you can just keep climbing and climbing and climbing, right? And we'll notice we don't actually add zero in there. The reason why is because zero, if you think about it, if I'm making numbers for the first time as a human being in I don't know, 2000 BC, it's really abstract to think of nothing as a number or have a number that represents zeros. And just like that, it also is kind of hard to think about adding negative numbers, right? And the idea is this, right? We have the naturals, so we do one, we can add stuff together, and we'll still stay in the naturals. But what if we do 3 minus 4? Well, you get something that doesn't exist. So the only way to alleviate this is actually adding in the negatives and zero. So there's two ways we can think about building upon our set of numbers. Either we can think of it as, hey, here's an operation that doesn't really work well. So in this case, it's subtraction. Subtraction doesn't really work well here. Or you can think of it as, hey, if I'm coming up with numbers, the most simple set is 1 and onwards, but then 0 is kind of abstract and negatives are kind of abstract. So let's add that in next. In this set, we call this the integers. This is what I've been calling the non-decimal numbers. And when you're doing odds and evens, the set that we consider are all the integers. If we go with the what operation fails, then you might think, okay, addition works, multiplication works now, subtraction works now. Well, multiplication used to always work. But now it's okay, but division doesn't work, right? For example, how do you recommend 3 over 5 or 3/5? I have 3 out of 5 volumes of an encyclopedia. How do we write this as a number? What do we need to do to our integers? And we literally turn things into ratios. We write things as a ratio with one number atop of another. And the formal definition is that it's all the numbers of the form a over b, where a and b are integers, but b is not equal to 0 since we can't divide by 0. And we use the previous definition to build upon this. We use the integers to, build upon what this is. And this is called a rationals, ratio rationals. But now there's something that's really interesting here. We always want to say that these numbers are in their lowest form. So while 6 over 8 does exist, the canonical version of it is 3 over 4. So we like to work with numbers in their most simple form. You'll see why in a bit, but it's just something that we have to keep a note of because it does actually come up later and it's actually a very useful thing. But some numbers actually aren't in here, right? Like pi's not in here, square root of 2's not in here. How do we add them in? It's kind of hard to add them in. This is actually surprisingly very complicated. So we just introduce a new set. We just call it the real numbers, and it's literally every number we can think of on the number line. And you might ask, we literally can't represent everything as a fraction, and no, it's not possible. And there's actually a really peculiar property here that's actually a little difficult to prove. We might do it later, we might not. So rationals will eventually repeat their digits at some point. So we call this property eventually periodic. So the rational will eventually repeat their decimal. So if you look at 13 over 3, we have 4.333333, and the 3 repeats forever. But real numbers never have to have their decimals repeat. So for example, if you look at pi, it doesn't repeat. Maybe now you can see how many numbers we're missing, right? This is a very interesting question, and we'll actually answer this later down the line. How many numbers are there in the rationals that are not in the reals? This is actually kind of all the content we need to go through for this episode. So because of that, we're going to do a classic proof. It's a little bit harder. The plot is like this. There's a guy, he's everyone at that time used to believe that rationals were the only things that are there. And this guy's hey guys, I made a proof, and the square root of 2 is not a rational number. And then they're hey, we can't let anyone know. So other people decided to kill him together. But then we know his name and everything. But yeah. But let's do his proof. And I think this proof is important for two reasons. You get more proof exposure, but how did we learn about this fact, right? It's a very interesting question to think about. So the first idea is that we'll assume that the square root of 2 is a fraction. Why? Because if it's actually not a fraction, we should be able to come up with a contradiction. So that is, we assume something that we're trying to prove is false, and hopefully going through logical steps, we'll be hey, wait, the thing that we assumed was clearly false, and everything else is true, so it must be false. So we call this a proof by contradiction. So we'll let the square root of 2 be a rational number, which means you can write it as a fraction in lowest form. So what does this mean? Well, we can just square both sides and then multiply both sides by b squared. Nice. So then we get 2b squared is equal to a squared. What does this mean about a? Well, we know that a squared is even, and because a squared is even, a is even. This is something that you can actually show. The reason why this works is because if you can show that a is even, then a squared is even. And if you can show that a is odd, then a squared is odd. So if a squared is even, it must be the case that a is even, because if a is odd, then a squared would be odd as well. And we'll talk about more about this relationship, but the idea is if a squared is even, we know that a is even. So let's write out a as an even number and multiply out, right? Let's say a is equal to 2k and 2k squared is equal to 4k. So we get 2b squared is equal to 4k squared. And then we can divide by 2 on both sides and get that b squared is equal to 2k squared. B squared is even, so b actually also has to be even. Okay, so b is even, a is even. What's the contradiction here? Rationals have to be in their simplest form. That's it. They just have to be in their simplest form. So this clearly didn't exist. And you could keep repeating this process over and over and over and over and over and over and over again as well as another way to think about this. And that's it. That's the proof. This is a contradiction, because how do we have a rational that's not in their simplest form? So it can't be irrational. It's a little tough. It's a little annoying, but it's kind of beautiful in its own way, right? And since this was a short one, I wanted to challenge you a little bit. The proof isn't really pivotal to anything, but the idea here is we always want to learn proofs to make our proof brain better, right? Having more examples of proofs and how they work always helps out. So that's why I wanted to prove this proof in here, even if it's a little tough to understand. So until then, I'll see you in the next one.